Hey there, math fans. Dr. Andy Love is going to talk about acceleration, velocity, and position. This is another way that curves naturally arise. Another important application of studying 3D curves. For most students, this is kind of new, but they've seen something like this in physics. In physics, you might say, we're going to study the x, y, and z components of velocity, or the x, y, and z components of acceleration. The biggest thing in this section is that acceleration is a vector, and we sort of are making sense of that. So I'm going to do two things here. I'm going to show you how we think about this so-called acceleration vector. I'll do a quick example in 2D and then a quick example in 3D with some visuals. So here we have Harry the Husky has been trying to hit me all day. I'm sitting over here at x equals 40. And he wants to hit me, but he's allowed to tweak his initial speed and angle and try to hit me, but he has been unsuccessful in doing it. So that's a motion problem, and it has both an x and y component of the motion. So what we're going to do to get us this, we don't necessarily need the full toolbox to do this, but let's assume this is a situation. This is acceleration. Now, if you really want to study acceleration, you need to understand all the forces, but I'm going to just start with this. So assume we're not being accelerated to the left and right at all, but we are being pulled down by gravity. You can actually picture that as a vector. So let me draw a couple little things on here. Right here. So there's this vector pulling it down. And it's always pulling it down. What's happening, you might say, why is it going up? Well, by pulling it down, what I mean is it's decreasing the velocity, and I'm going to show you that in several things. So even if you can have an initial positive velocity, it's just going to decrease by that much each second. The way we work from here is the same way we did in Calculus 1. We integrate. So the integral is negative 32t, but then you need some sort of initial condition, which is what Harry's trying to figure out here. What does he want his starting velocity to be? That's the question here. His starting position, we're going to say Harry threw it from 0.6. So we'll say when he left his hand, it was 6 feet high. So you get these equations for motion. He's trying to hit me. He wants to tweak A and B. So that should feel kind of similar to Calculus 1, but some interesting things, because I'm just sort of stating a problem. You then put in your initial conditions and you say what you need. And what you need is that it's going to hit me. So it's going to hit this point. Let's pretend I wanted to hit this point 40, 0 at some time. So that's not really part of this section. I just wanted to ask an interesting question. So I want this to be 40. The x-coordinate needs to be 40 at the same time when the y-coordinate is 0. So we'll do that first, and then I'll talk about this. If you combine those, there are many correct solutions. And so then you need to either add some other criteria or pick a number. So let's add the criteria that he's going to throw it at a certain angle. Let's have him throw it at 45 degrees. So if he's going to throw it at 45 degrees, then that's a different question. Again, that's not really what this section's about, but now it's 45 degrees, and so these two things are going to be the same. If it's some other angle, then you can state these in terms of angles, which is often a good way to go. You say R. This is more kind of things we did at the beginning of the term when we were studying vectors. So there's always these, the moment you get to an application, there's these practical concerns of what would be easier. Would it be easier to give Harry the angle and the speed? Yeah, I think so. But I'm going to leave it as this because that's what I have to tweak. Okay, that's interpretation stuff. So let's assume A and B are the same. If you do that, then you can completely solve this. And I did, and I got that A and B, if they're the same, have to be 23.59. And then I figured out based off of that what the speed would be. So the speed being the magnitude of this. So I just wanted to start with this as an example, something where I actually do some solving. So square root of a squared plus b squared, I got that it was about 33.36 feet per second. Okay, so if he throws it a little harder, 33.3 initial velocity, I have the initial velocity there on the left, he'll hit me. It needs to be 45 degrees. Okay, that's going to be pretty close. So now what I'd like to do is just talk about a few things. So all I've given you is the acceleration vector in the picture so far. So let's talk about the vectors for a moment to help clarify a few things. Okay, so now I'm going to draw the curve. So there's the actual curve that it's traveling along. I was just showing you the object being thrown. And let's show you a few other vectors. So why do we think of accelerations? Why is that the derivative of the velocity? So as it moves, let's do something here. I am going to show you the velocity. So there's the velocity vector. The length of that vector is the speed. So it's slowing down, slowing down, slowing down, slowing down. It's at the top, speeding up, speeding up, speeding up, speeding up. Okay, so what the derivative of the velocity is doing is it's measuring the change. It's saying, okay, there's the velocity. What happens if I go forward slightly in time? All right, so let's go forward slightly in time. There I'm gone forward just a very small amount of time, and I've redrawn this vector. What we'd like to figure out is how much it's changed. How much it's changed from tip to tip. The only problem is the vector's not tail to tail. So what we do is a couple things. So first we take that vector and we shift it back. And now we're going to compare the velocity at a certain time to the velocity a moment later, 0.1 seconds later. And we're going to draw a vector that goes between them. Sorry, I didn't have this ready. So let's do this. That vector. That's the change. So I do this in class. I talk about this. I just wanted to show a physical model. I talk about how when you take the derivative, you're measuring that change. If you take the derivative of the blue vector, the velocity vector, you're measuring the change over the next moment. It's that change divided by time. Now, we don't usually draw the vector there. We shift it back. So let's shift it back. Fun with animation there. And then we divide by time. Dividing by time rescales it. So let's do that. And that happens no matter where you are. You get that it's pulling down. That's what velocity is. So if I move forward slightly, we could play the same game. Let's go forward slightly in time. And let's say we want to measure the change. Again, what we do is we compare the velocity, the blue vector, at a given time. Let's go back. Let's move it back over here. So we have some velocity slightly forward in time here. It can be further away. But then it's going to be a little less accurate. So usually it's a small thing. And then we say if we shift that back so it's touching, and we compare how those vectors have changed. So let's draw that now. And then if we shift that back over here, notice it points straight inward because we're at the top. And then I can rescale it by dividing by the time. That's what acceleration is. It's the change in the vectors in that sense. So I just wanted to show that because I thought that might be interesting. So when we talk about the derivative, that's the visual change. That's that little orange vector we're thinking about when we're taking the derivative of a vector function. So that's what the acceleration is measuring, is that direction. The reason it gets longer is you're dividing by time. In this case, it's constant. It doesn't matter where we are. Our turning and changing of velocity is this same thing. That's why the second derivative points this way. We talk a lot in class about, I'm going to show one other thing here. about this idea of what I like to call measuring sticks. We have a vector that points straight inward and forward. That just helps me see that the following observation. So initially I'm slowing down. You can see that because the acceleration is behind the normal direction. When I'm at the top, the acceleration is in the same direction as the normal, and then it's in front. So I find that this all helps me understand what's going on. So that's how I think about acceleration. The truth is, acceleration arises from the study of forces. So if you go into your physics course, they're going to give you a bunch of forces. Once you've added up all the forces, you'll say, this is mass times acceleration. Then you'll say acceleration is 1 over mass times the forces. I know I'm run into my screen there. So that part is, to me, the hard part. You'll have to read a lot, do a lot of research, find out all the forces, find out how to describe them, see what they depend on. Do you want to deal with air resistance? That is the challenge. Once you're there, then you have the second derivative. You integrate component-wise. Now, sometimes that can be hard. So that's the game we're playing. Okay, so let's do one more. So sorry that we helped Harry do that. So here's a 3D example. And I'm going to add something to this. I'm going to add another force. So let's erase here for a second. Let's assume there's a really strong wind blowing west to east. So from above, and we could spend a long time thinking about, as soon as you make things applied, it can be really challenging. But let's assume we have a strong wind blowing this way. And this is the X, Y, Z plane. So we're calling this north and west. This was the view from above. So we have gravity pulling us down. So we'd have the force due to gravity, which would be something like 0, 0, negative mg. G is gravity, m's the mass. And then we'd have the force due to the wind, which might be something like pushing, let's see, what did I say? East to west. Yeah, so I'd have something like this. So just to make it look a little bit like a physics question, you would add those two things together. You would divide by m. That would tell you your acceleration. You can integrate and figure out what's going on. So I've made this is actually a 3D thing. And I have this person standing out here. So there's me again. We're going to try to hit me with the water balloon. But let's now let this wind be there. So the wind is going to make it accelerate this way. And then you can play all the same games. You could allow me to tweak my initial velocity until I hit it. Almost there. You can tweak this one. I made it so that there. That'll hit me. Okay, so whatever. That'll hit my feet. Oh, we don't hit his feet. Anyways. But in terms of, we still think of it the same way. So if we fire this thing in the air, we still have these same vectors. We have the velocity. The blue vector, let me see if I'm actually graphing. Yeah, the blue vector is the second derivative. Did I? Yeah, okay. I gave it correctly. I'm throwing it very hard. That's why this looks different. Anyways, did it stop? Oh, it did stop because I didn't go far enough. It's going to go way too fast now. I scaled this too much. Okay. Boom, it'll hit me. So as it's moving, as we were seeing there, we can talk about the same things. And here it's even more valuable. The acceleration points in the way in which the velocity is changing. There's that. Let's let it go again. And then we can ask various questions. So if we put our measuring sticks up, meaning if we put our unit tangent, our unit normal, Let's put those there. I'll make them a little longer so we can more easily see them. All of those are in the same plane. We call it the osculating plane. And you can then look at things like this. Let me get this thing going again. You can see that my acceleration is behind, the blue vector is behind the red vector, and then it's in the same direction, and then it's ahead. I'm speeding up, I'm speeding up, I'm speeding up. So I feel like that really helps me understand acceleration. I hope that helps you.